Hey guys, today we're going to take a look at some properties that logarithms have. So some of these we've kind of discovered just doing other examples, like in this top box right here. The log of 1 is always 0. Okay, that's just a property. Why? Well, because any base to the 0 power is always 1 as an answer when you think of it in terms of exponents. So the log of 1 will always be 0. The log base A of A would be equal to 1. Okay, so if this base and that base are the same, essentially they're going to cancel each other out. So again, think of it as an exponential. A to the first power would always equal A. And using that kind of thought process, if you look at this one, this is the log base A of A to the R power will always equal the R. Well, again, you can think of this a couple different ways. One is that this log base A and this base A cancel each other out because they're inverses of each other, which would leave you with the R. Or you can rewrite this as an exponential. This base to that power is going to equal that base to that power. Okay, so that's just some properties. So if you look at these examples down here, using these properties, you can simplify these. So like, what is the log base 7 of 1? Well, the log base anything of 1 is 0. That's it. Okay, what is the natural log of E? Well, remember, natural log means base E. So what is the log base E of E? Well, they're going to cancel each other out, and you're going to get a 1. The next one, what is the log base a half of 1/2 to the 20th power? So I purposely gave you some weird numbers here because the numbers don't matter. As long as they're the same, they're always going to cancel each other out, and it's just going to leave you with the 20, with that exponent. Same with D. The natural log of e to the third, natural log means base E, so that's going to be 3. Okay, so just some kind of straightforward properties that pop up every once in a while. The next set of properties are maybe not quite as straightforward, but they're pretty important when it comes to being able to solve equations, which we're going to do later, where you need to maybe take a logarithm and rewrite it as a couple logarithms, or maybe you need to take a couple logarithms and you need to simplify it by writing them together. The first one says, so if you read in words, it says the log of a product. So we're taking the log of two things that are multiplying each other, a product. The log of a product equals the sum of the logs. So the log of m times n is equal to the log of m, the first one, plus the log of n. Now, that may look kind of weird as to why these two things would equal each other, but again, logarithms are exponentials. The answer, the solution to a logarithm is an exponent. So they're actually going to follow the rules for exponents. So if we think, what is a to the m power times a to the n power? Okay, when you're multiplying variables, what do you do to the exponents? You add them. Okay, you get a to the m plus n power. That's the exact same thing that's going on here. Okay, so these are exponents. They're being multiplied. So I can write them as an addition problem. I can add those two things together separately. Okay, and this goes back and forth. Okay, we need to be able to go both directions. So if we have a product, we can rewrite it as the sum of two separate logarithms. But if we have two separate logarithms, we can rewrite it as a sum, as a product. I will say that actually going from this direction to here is probably going to be more important to us moving forward, like when we solve equations and things. Okay, the next one says the log of a quotient, so you have a division problem, equals the difference of the logs. So again, this goes back to AM divided by AN. If you are dividing two variables, you subtract the exponents. You take m minus n, and that's your answer. You can also think of it as, remember, if you have something in a denominator, that's like a negative exponent. Okay, if I take this a to the n power and move it up to the numerator, it would become a to the negative n power. So anything in the denominator is like a negative exponent. So if you notice, these two are in the numerator, they're both positive, and they get added together. This one's in the numerator, so it's like a positive exponent, but this one's in the denominator, and it's the only one that ends up being negative. I feel that's a neat little shortcut to think about these. Okay, this n that's in the denominator of a fraction ends up being a subtraction because it's essentially a negative exponent. Okay? And again, I'm going to show you examples of all these and show you how it works. Okay, the last one. The log of a power equals the product of the power and the log. Now, those words aren't going to mean anything to you. Okay, here's what it says. If you are taking the log base a of m to some power, I can take the power and I can bring it out front and write it as a multiplication. Well, why? Because if you take a power to a power, okay, so that's the exponent rule, you multiply the two exponents, right? If you have a to the second and then that's to the fifth, you'll end up with a to the 10th. You multiply the two exponents. So a to the m times r. Well, again, this is an exponent. It's being taken to an exponent, so you can write it as a multiplication. They make it more clear. I mean, technically the r could just drop down and you could write it as a multiplication this way. This way they're making it more clear. They're taking the r, they're bringing it out front, and they're writing it as a multiplication problem. Okay? So these three rules are the examples we're going to look at next. Okay? So the first one says, write this problem, log base 2, of 4 times the cube root of x minus 1 as the sum of logarithms. So this is a product. 4 times something. Okay, these two things are multiplying, so we're looking at this rule right here. And we want to write it as a sum. So we're just going to take these two and we're going to split them apart. We're going to write it as the log base 2, keep your same base, of 4 plus the log base 2 of the cube root of x minus 1. Okay, we had two things multiplying each other, and now we've split them apart. Now, there's a couple simplifying things we can do here. This one simplifies the log base 2 of 4. What exponent would you raise 2 to get 4? Well, that'd just be 2. So that simplifies all the way down to just a number. But this one we may have to think about. If you look back at the directions, it says express all powers as factors. Well, that's this rule. This rule says if you have a power, you can write it as a product. Well, products mean you have two factors. So what they're wanting us to do is, this cube root, this is a power. Let me come over here for a second. The cube root of x, just plain x, is equal to x to the 1/3 power. So this expression, this x minus 1, when you see this cube root, this is actually a 1/3 power. And so I can take this power and I can bring it out front. And that's it. So I can rewrite this as 1/3 log base 2 of, and then I've got x minus 1. That's it. Okay, so that's as simple as that gets. Take the product, split it into 2, simplify this as much as you can. Simplify this. This doesn't really simplify, but we can take the power and we can bring it out front. And that's it. That's all. We're just following their directions. Okay? Look at the next one. The next one is a division problem. Okay, so we're going to be using this rule. The log of a quotient. So we're given a fraction, and we're going to split it into 2 logs. Okay? So I've got two things. This is a thing on top, and this is the thing on the bottom. So the log base 6 of x to the 4th, and then it's going to be minus the log base 6 of x squared plus 3 to the 2nd. The only thing we can do with this is we can express the powers as factors. The thing that we're taking the log of, this x, is being taken to the 4th power. So I can bring the 4 out front, minus, and the thing we're taking the log of, which is this x squared plus 3. This whole thing is what we're taking the log of. This thing is being squared, so I can bring that exponent out front. 2 log base 6 of x squared plus 3. Now, this is all connected together. This is not, we can't do anything with this exponent. This exponent is just kind of stuck here, okay? This is the exponent that was connected to the entire thing we were taking the log of, so we can take that entire exponent out front. This is your final answer. There's nothing else you can do with that, okay? Okay, now on the back, I'm going to put all those properties into one problem. So here's what I've got. I've got the directions say write the natural log of, and they've got this huge expression as a sum and difference of logarithms. Okay, so what I have is actually there's 4 things here. Okay, there's an x cubed. It's multiplying the square root of x minus 2. So these 2 things are multiplying each other. So I've got 2 things there. Then I've got, in the denominator, I've got a 5 times, okay, these 2 things are multiplying each other, this x plus 1 squared. So I've got 2 things up here and I've got 2 things down here. So when I rewrite this, I'm going to write it as 4 separate logarithms. Okay, so each factor is going to become its own logarithm. The easiest way to think of this is the fact that anything in the top, anything in the numerator is going to become a positive logarithm, and anything in the denominator will essentially be a negative logarithm. Think of it as a negative exponent, so that's going to be a negative logarithm. If I think of it that way, then I can write this as the natural log of the x cubed, and then plus the natural log of this square root of x minus 2 thing, square root of x minus 2. And then these 2 are going to be separate logarithms, but they're both going to be minus. So it's going to be minus the natural log of 5, and then it's going to be minus the natural log of x plus 1 squared. Now some students think that these 2, that this should be addition, because these 2 things are multiplying each other, and when you multiply 2 things, you can rewrite them as addition. And that's correct, except that then after you do that, the fact that they're both in the denominator, there is a negative out front that will then get distributed in, and so this one will become a negative. So I think this way is just kind of easier to look at. Anything in the bottom is a negative, think of it as a negative exponent, and then write it as subtraction. Now, there is one more thing we can do. We can express all the powers as factors. So we're going to take all the exponents and we're just going to bring them out front. So this will be 3 natural log of x plus, remember, square root, that's an exponent. It's x minus 2 to the 1/2 power. So we're going to bring this radical out front and we're going to write it as 1/2 natural log of x minus 2 minus, well, this is just the natural log of 5, nothing to do there. And then I've got this exponent of 2 that I can bring out, minus 2 natural log of x plus 1. And that is it. That is the final answer, where we've taken this expression and we've pulled it apart into separate sum and differences. Okay? Now, what's actually more helpful usually is being able to go the other direction. So take a look at these problems. I've got 2 logarithms. They're being added together, and I'm going to go in the opposite direction. So the first thing you want to do is, if you have a number out front, so there's nothing here, but there's a 2 here, we want to take that 2, this product, and we want to rewrite it as an exponent. So I want to take that 2 and attach it back to the 2. So log base 12 of 3 plus the log base 12 of 2 squared, or 4. Okay, now I've got a sum. I've got 2 separate logarithms that are being added together. I can rewrite that as a single log where the 3 and the 4 are multiplying. 3 times 4. Okay, that's the rule. 2 separate logarithms could be rewritten as a product. So I've got 3 times 4. But 3 times 4 is 12. And the log base 12 of 12 is going to be 1. That's one of the properties we learned. And that's it. So this entire expression simplifies down to just the number 1, but we couldn't do that here. We had to do that simplifying to it so that we could see what would cancel out. Same on this one. Okay, I've got a 1/2 out front, so I'm going to reattach that as an exponent. So that's going to be a square root. I've got a 2 out front. I'm going to reattach that as an exponent. So that's going to be a squared. And I've got this subtraction right here. So that means this thing and this thing are going to be dividing each other. This one that's negative, it's going to be down in the denominator. So it'll be, I'll do this in 2 steps. Log base A of the square root of 4 minus the log base A of 5 squared. Now I'm going to rewrite this as a division problem. So log base A of the square root of 4, so that's 2, and then over 5 squared, so that's 25. And that's it. That's your answer. Okay? Look at this one. This one, it looks crazy. I've got a log, I've got another log, and another log. So this is kind of like this problem, except I'm going the other direction. I've got 4 separate logarithms. I'm going to rewrite this as 1 logarithm. Okay? The first thing I'm going to do is I'm going to reattach these numbers out front. I've got a 2 out front, so let's reattach that as an exponent. I've got a 3 out front. Let's reattach that as an exponent. Alright, that's it. Now, I'm going to write this as a single log, log base A. I've got a positive logarithm, I got a negative logarithm, I got another positive, and I got another negative. So I'm going to have a fraction over here. Anything that's positive is going to be in the numerator, and anything that's negative is going to be in the denominator. So this 6, because this is a positive logarithm, is going to be in the top. This minus log of 3 squared is going to be in the bottom. So that's 3 squared, so that's a 9. This x minus 1 cubed is positive, so it's going to be in the top. So let's write this as x minus 1 cubed. And then this x minus 1 that's all by itself will be in the denominator. Okay, now, once I rewrite them, and this is just one simple fraction, I can use just normal reducing that you could do with any fraction. Okay, this is going to be equal to the log base A. The 6 and the 9 will reduce. 3 goes into both of those, so that's 2 over 3. And then I've got an x minus 1 cubed over just an x minus 1. So I've got a factor down here that's going to cancel one of these factors up here. And I'm going to be left with x minus 1 squared. And I think we can stop right there. That is our final answer. So we're rewriting multiple logarithms as a single logarithm. Okay? The last thing we're going to talk about is something that's called the change of base formula. Now, in class, what we would do is I would ask you to kind of approximate what you think this answer is. Log base 3 of 12. Well, what exponent would you raise 3 to get 12? Well, most students know that 3 squared is not going to be big enough, and that 3 cubed would be too big. So it's got to be somewhere in the middle here. So most students will say, like, I don't know, 2.5. They'll say, they'll say it's to the 2.5 power. Well, if you take your calculator and you take 3 to the 2.5 power, you'll get 15 point, let's say 6. Okay, so too big. So we need something smaller, all right? So 2.4, how about that? And so they take 3 to the 2.4 power. 13.96, almost 14. 14.0. Still too big. All right, so then is 2.3 going to be good enough, or do I need to go down to 2.2 maybe? And so they'll try 3 to the 2.2 power. We get 11.2. All right. So if we kept playing this game, we'd get there eventually. Okay, we'd kind of narrow it down. So maybe 3.2 or 3 to the 2.25 or something. And we try, and finally we'd get close to 12. Well, there's a quicker way to do it using your calculator. Your calculator, for most of you, your calculator doesn't know what log base 3 is. It only knows log and natural log. So there's something called the change of base formula. And what it says is the log base A, so this could be anything, of m is equal to the log of m. So you take the log, so this is like the common log that's on your calculator. You take the log of m, which is the bigger one, the one that's up top, and you divide it by the log of your base. So this number that's down low gets put down here in the denominator, the log of m over the log of a. You can also use the natural log. It works the same way, as long as you're consistent. Either use the common log button twice or use the natural log button twice. Now, if I had done that up here, and I had done the log of 12 divided by the log of 3, okay, so log of 12, parentheses, divided by the log of 3, parentheses, I'm going to get 2.26. So we were getting close. 2.26. What do we have? 2. Okay, so if I would have taken 3 to that power, that's how I would have got 12. Okay, so instead of playing this guessing game, you can use what's called the change of base formula. So for this example, what is the exponent you could raise 7 to get 35? Well, you take the log of the 35 over the log of the 7, put that in your calculator, and that's going to give you your answer. So, and again, you can use the natural log button too. So the natural log of 35 divided by the natural log of 7, and you're going to get about 1.827. 1.827. Okay? Okay, the next one looks a little weird. Got a radical and it's got a fraction. Doesn't matter. Take the log of radical 2, you can do that in your calculator, and divide it by the log of 1/3. You can do that in your calculator. So, log of radical, 2. Now, notice that my log has a set of parentheses, and then when I hit the radical, I also have a set of parentheses. So I'm going to use 2 parentheses to close that off. So now the top should be closed, that log should be closed. And then I'm going to divide that by the log of 1/3. So I'm going to go ahead and use my fraction button, 1/3. Again, close that. And I get negative, so negative 315. And that's my answer. Okay? So take a look at the worksheets, and if you have any questions on the properties or the change of base formula, please let me know. All right, thanks guys.